And now I wish you lots of fun and new information.
Okay, thank you, Andreas, for the introduction. So now we start with the webinar for the RIGID.flex 2F-xRi technology. So an attractive RIGID.flex variant. So the topics for today are the first point. I would like to speak a little bit a general overview about the RIGID.flex technology. Then my second point, then we come in our main topic for today. It's the 2F-xRi technology. Speak a little bit about standard stacks, the manufacturing process, then about signal integrity, the combination with the HDI technology in this case, and at the end about some mechanical options like liftoff and sieve technologies. Yeah, and my last point is about the capability of Würth Electronics. Yeah. So my name is Würth Elektronik and I work here in the technical project management. Yeah. First, a little bit of overview. So we at Würth Elektronik speak a lot about, I would say, standards. So standard is for us, I would say, a standard stack up, standard materials, standard design rules, and so on. That means for us, so if you are designing your flex rigid PCB according to our standards, so you will have, I would say, the best performance, the best price, and we will have at the end, I would say, no problems in our production for the manufacturing of this PCB. Yeah, if you are using our standards. But we, or not but we have also additional technologies. We have individual solutions for you, but we say in general that we should speak about these individual solutions here. So we tell it then, or we say to this then it's maybe a project, or we need to be in discussion with you as our customer, yeah, to get, due to this cooperation, and yeah, the perfect quality, the reliability of the product, and at the end to save costs. So we in general recommend that you contact us already at the beginning. That means at the product idea or the concept or the design phase, that you get in contact with us, that we could give you, I would say, tips and tricks regarding our experience, that the product, yeah, has the best performance and also the best cost for it. So in general, we have a big standard. If possible, use this. If our standard is not enough for your product, contact us and we could speak about your, I would say, individual solution. The system view. So at the end or at the beginning, mostly, you get a, I would say, a room and a functionality given by your marketing, your other departments, and you as the layouter have to get all this stuff, all this PCB, all these functions inside this room. So now the question is at the beginning, which technology you are using maybe to get all this inside. So we've got here on the right upper side a modular solution. That means two rigid PCBs which are connected by a connector, and maybe this is soldered inside the two PCBs. So a modular solution. On the middle one, we have I would say an homogeneous solution. It's a pure flex rigid PCB. So PCB 1 and PCB 2 are connected by a flexible area. Yeah. Or the third thing is I would say, partly modular solution. That means if I have, I would say, on the one side a rigid PCB with a flex end, and maybe here another rigid part with a connector, or maybe a sieve contact to contact the other PCB. So this solution is mainly used if the two PCBs have, from technology side, a real big difference. So we have on the one side maybe a 4-layer, and on the other side maybe a 10-layer HDI PCB. So then then normally it's done as separate PCBs, because if I would do it as a total flex rigid PCB, the complex HDI technology and flex rigid combination would would take a big area, I would say, on our production panel, and the costs will go up. And the second thing why using this modular solution is if you have maybe such a standard solution and here a customer specific PCB, which you can change from customer to customer. Okay, what is your, I would say, main thing then is also to get the perfect area with your PCBs. Maybe, so it's always the amount on PCBs we are getting on our production panel where we are producing this PCB. And this is then divided by the PCBs, and so we are getting the cost. So a perfect design or a perfect routing of the flex areas will save costs. You could see here, this PCB here now on the flat version, and I would say due to bending processes, it is then installed like here in this 3D model here. Yeah. So in general, we say the flex rigid is not a pure electronics thing. So it's a real big impact of mechanics and on the other side, the electronics. Yeah. If you now know which technology you're using, we come to the next step. You have to define which stacker you are using. So these are our, I would say, our classic stacks. So the standard stacks. On the left upper side now, we have this 1F-xRi technology. 1F-xRi means, so the 1F stands for one flexible layer, one flexible copper layer, and this flexible layer is on the outside of the PCB. And this xRi stands for, I would say, X layers in the rigid area. So in this case, we have 1, 2, 3, 4, 5, 6, 7. So in this case, we have a 1F7RI PCB. So one layer flex outside, and in total 8 layers in the rigid part. If one layer isn't enough, a second layer comes on it. So then we have the possibility of a 2F-xRi. This technology we will go in deeper in the following presentation. The other option to have 2 flex layers in the flex part is to put the flex layers in the middle of the PCB. So you could see here we have xRi, in this case 3RI, 2F, 3RI PCB. So also 8 layers in the rigid part, 2 layers flex, and these 2 layers flex are in the middle of the PCB. Our last standard stack which we have is now a xRi 4F-xRi stack. That means now 4 layers in the flexible area, like you can see here. These are 2 flex cores with 2 layers, and these 4 flex layers are glued together with a bond ply in the flex area. So a bond ply is a polyamide foil with 2 sides and adhesive. So it's also perfect if you have impedance requirements that you're having through the whole stack here or the whole flex area, defined the electric distances to get maybe impedance signals over it. So these are the 4 classic stacks, and I would say around about 70 to 80% of our production are, I would say, filled with such standard stacks. Yeah. So now we come directly to our first poll. So what we would like to know is the rigid flex technology already in use in your company? You have here now 5 answer options. So our multiple answers are possible. So the first is no, no, but there is potential. Yes, flex layers inside. Yes, flex layers outside. Or yes, but we are using also or this semi-flex or bend flex technology where the bending area is based on the FF4 material. So the poll is now coming.
Okay. We have already 40% of the answers. 60%. You're very fast today, maybe due to the fine weather. Yeah, we just wait a few more seconds. We are approaching 80%. Okay. So 5 seconds left for your answer, and I will close the poll now and show you the result. So actually 5% of our participants are not using Flex Rigid, but 36% see potential for the technology. And we have users with Flex inside 35%, Flex layer outside 40%, even more, and semi-flex or band flex technology 16%. So that's quite interesting, and yeah, I'm looking forward to the 36%. They are having potential. Okay. Thanks a lot for it.
Thanks for the answers. Thanks, Andreas. Then we go on with the presentation. So now we come to our main topic. It's the 2F-xRi technology. And first, I would like to speak a little bit about the standard stack, what we are having. So in general, we are using the base material FO4 is a TG150 degree, halogen-free and filled material. Filled means that it has less Z-axis expansion. The flex material itself, we are using only polyamide material, so we don't have flex materials like polyester and so on. And if you don't give us any thickness in your stack or in your specification, we are using a 15 micron thick polyamide, and we are also using for this stack up only adhesive-less polyamide materials. Also standard is that we are using on the second side, I would say on the second side of the flex, so the layer 2 in this case, we're using always a cover lay foil. Cover lay foil is also polyamide foil with an adhesive, and as you can see here, it's only partial inserted. That means the overlapping of this cover lay is on each side roughly 1 millimeter into the rigid part. Yeah. On the outside, as you can see here, we are using, I would say, a flexible solder mask, also partial on the flex area with, I would say, an overlapping on the rigid area. Also, what we are using as standard is the inner layer copper base thickness is 18 micron copper. On the right side, you could see here our standard stacks on our web page. So these are also possible as digital stacks, which you could load directly in your EDA tool. Yeah. So these are the thickness which are inside. If you need another thickness or you have another thickness recommendation, then contact us. Then we could support you with a stack up. So this is the standard stack, but this standard stack could also be modified. So we are also having different polyamide thickness. So instead of the 50 micron, maybe if you have impedance requests, we are using a 75 micron or 100 micron thick polyamide. Also possible is 35 micron on the inner layer as copper, and also the combination with microvias 1x1 is always possible with our standard stacks. Yeah. You could see here a cross section. It's now a stack with 2F-xRi. That means 2 layers flex in the rigid part and 2 layers in the flexible part. And the rigid part, we don't have any more copper layer. It's only for mechanical that the panel or the PCB gets more stable in this area. Here you can see the cross sections. So it's now a microvia through the 75 micron thick polyamide material. Diameter is here 100 micron. The upper picture here is for a non-filled microvia. You can see here this dimple. And this picture here now is for a copper-filled microvia for soldering directly on it. Another modified thing is the cover lay. As I said, standard is here on the outside a flexible solder mask, but it's also possible, like the picture here, with a cover lay foil on the outside. Yeah, you can see here this PCB, one connector, flex part with the impedance lines over, and on the other side is the other connector. So it's a pure connector interconnection, I would say. Difference between flexible solder mask and cover lay is, so flexible solder mask, it's a little bit easier for us for the manufacturing process and a little bit cheaper, I would say. cover lay, a little bit more, or it's more expensive than the flexible solder mask, but has benefits, I would say, in if you have maybe a dynamical bending situation, you need a dielectric strength, maybe a higher dielectric strength of this solder mask or of this cover lay. So cover lay is here much better. The manufacturing process of such an 2F-xRi PCB. So we have here some process stacks. You could see here I would say really yellow marked are flex specific, and the rest are, I would say, standard processes for multi-layers. Yeah. We have on the one side here the low flow prepreg, which is inserted here directly under the flex area. So the difference in between a low flow prepreg and a standard prepreg is only the low flow prepreg don't has this resin flow like a standard prepreg, so it's already older, I would say. So yeah, the resin flow isn't that much like a standard prepreg. And in this prepreg, we mill a window inside directly there where the flex part is. And due to the smaller resin flow, we don't want to have that the prepreg is now flowing again in this area and glue it together. So this area must be free here of prepreg. Then we have the standard inner layer cores, which the photo imaging, the etching process, and we always have the one core which is under the flex area. This has such small depth routings. You could see here a cross section. So these depth routings are roughly 200 micron deep. And the reason for this depth routing is at the end, we are coming with a depth routing process from this side and going here to the top of the other depth routing, I would say, that we don't hurt the cover lay material here. It's because of the tolerances of the depth routing. And at the end, the material here under the flex area is falling out. Then we also have here the flex core, which is now here on the top layer with 2 layers copper. Yeah, also we are doing the standard inner layer processing, and then we are putting here this cover lay film on it. This is I would say, a handmade process, and then also fixed and pre-pressed, I would say, on this flexible core. I would say after this process, after this multi-layer lamination, this PCB is handled like a standard multi-layer PCB with the drilling, the plating processes, the etching process, and so on. The only special thing at the end is that we have the depth routing here, and we are putting a flexible solder mask or cover lay on top of the flex area. So as you can see, the handling our production are mainly, I would say, standard multi-layer processes. At the beginning, a little bit differences, but the main processes are the same. To get all the things a little bit easier for production, as I said, this cover lay is fixed or registered manual by hand. So it's always better, if we reduce, I would say, this effort and also the cost at the end. That means we try to do not every cover lay for each flex area, I would say, partial on it. That means we are trying to build such an array. Yeah, that means we are putting only one array here, fixing it, pressing it, and it's much easier than handling all the flex areas several. So it's a thing of effort, handling, and at the end, the costs of the PCB. This is for, I would say, longer flex areas, for short flex areas. So here it's critical to connect, I would say, it with a cover lay. There we recommend to have a distance maybe of the rigid part of min 4 millimeter that we could connect this cover lay area here. So, and it's always a benefit at the end in the costs and also the performance. Good. This was now a little bit about, I would say, the manufacturing process. Now we come to the advantages. So where we have the main advantages in this 2F-xRi technology, you could see here on the right side, PCB was, I would say, flex areas here and a USB connector, and we have to go here from this component with impedance signals, impedance traces to this USB connector. And we don't want to have any more connectors, and also a saving of footprint. So in this case, we have a 3RI, 2F-xRi stack. That means we have both components on the outer layer, and now the signal must go by this through-hole via down to the flex layer, over the flex part, and back to the top layer. Yeah. With the 2F-xRi technology, the signal transmission can go directly component copper over the flex part and to the USB connector. So the signal transmission in this case is much better. And we don't have any more, I would say, impedance jumps due to this bladed vias. Yeah. Also, what is also perfect, we can contact maybe the reference plane, maybe on layer 2, directly by micro vias. Or the other thing is, if we have maybe a complex VGA or something on the outer layer, we could go directly with the signals on the second layer and go with the signals over the flex area on layer 2 and have the ground shielding layer maybe on the top layer. So real big advantages here in the signal transmission from, I would say, component A or rigid part A to rigid part B. One more option to get here a little bit, or some tricks, I would say, is in hatch. In hatch are, I would say, copper openings in the reference plane. And this copper openings has, on the one side, I would say, yeah, improvements on the flexibility, improvements for drying of the flex material, because the polyamide is a microscopic material and you have to dry it prior to the soldering process. And due to these openings, so the drying gets better, yeah. And the next point for this hatch or improvement is that due to this hatch, the impedance is increased, yeah. The impedance is going up. That means at the end, we have a compromise. We could use maybe a thinner polyamide material, which gets a better bending to reach, I would say, at the end, the same impedance. In general, we say if you have critical impedances, or we will say at the end, if it's going up to 5 to 6 gigahertz, so you should not have this hatch anymore. So then you should have a solid reference plane with copper. In this diagram, you could see now we have here, for example, a 50 micron polyamide. We have differential microstrip, and you could see here the copper percentage of the crosshatch with 100%. For example, you have here 78 ohm. With 75%, you go up to 85 ohm. So the impedance is going up with less copper. But in general, we don't recommend to use less than 50% copper coverage of the reference plane. So at the end, it should be more than 75 to get the perfect, I would say, also the impedance there from the one to the other part. That's also compromises. Compromises is, for example, this here to have both functions inside. The hatch better for the bending. So in this here's at the end the flex area. We have then here the hatch for the better bending, I will say, and the better drying, and the impedance signals have a full ground cover directly under it. So what could we offer for the 2F-xRi, or in general, I would say for the flex rigid technology? We could provide for you this calculation, and this is also then perfect for your documentation in, I would say, in your PCB specification. Yeah. Okay, we are using, only for information, we are using this polar speed stack, and with this program we could also calculate this hatch. Okay, this is now the point to the signal integrity. Now we go on with the HDI combinations. So this is now a, I would say, standard stack. Micro vias, as I said, is possible, modified stack. But then if it's getting more, that we need maybe a buried via from layer 2 beginning or a micro via from layer 2 beginning, it's not possible with this 2F-xRi technology, or I would say with the standard stacks, yeah, because we are pressing a core on the outer layer, and on this layer 2 of the core, we cannot begin with, I would say, a tooling process and plating this via. So at the end, we are needing here a little bit another solution. As I explained, we are also producing PCBs with one flex layer on the outside, and we are now doing this process twice. So you could see here, it's a 2 times pressing. We have the first pressing here. It's a 1F-xRi, the first pressing. We are then making the micro vias, third vias inside, filling this. And the second step is then pressing once again and 1F with a pre-preg, and on the other side, pre-preg and copper foil on this 1F technology. So at the end, we have a 2F-xRi also in combination with the micro vias and Würth vias. On the next slide, so here now we could see some cross sections here. Here now, I would say 2F-xRi PCB. So currently here's no copper, but here you could see a cross section of the flex part, the reference layer here now on top, and the differential signals on the second layer. Also, you could see here the cover layer on the outer layer, which overlaps here on the standard solder mask. So we have here a 2F-xRi stack with a 1-2B1 stack. So one layer micro via and the Würth via over 2 layers. Also, we always need to fill this Würth via layer. It's according IPCs this type 5 with resin. Here one information. This is all the micro via Würth via layouting is based on our HDI design rules. But the HDI design rules cannot be combined one-to-one with the flex rigid technology. The reason is the different materials, different dielectric distances. So if you have such a, or you need such a solution, come to us, we could speak about, we could define a stack up and also define a little bit other design rules, I would say. Okay, this is for the HDI technology. Then we come further on to the mechanical options. So one mechanical options is the flex lift-off technology. That means the flex begins already, I would say a little bit earlier, the bending, and goes not directly till to the border of the rigid flex PCB. The main advantage is maybe a housing is here and the flex cannot go out here. And the second point, what is a advantage is you could also have maybe this top layer here also for assembling, putting components on it, and so on. Another perfect option for this flex lift-off technology is coming now here. It's always used or often used, I would say, for dynamic bending applications. It's for the rolling movement, so that we have a defined bending. So it's rolling here on this lift-off area up and down this flex cable. So in this case, we have more than 1 million bending cycles. This is the stack of this PCB. As you can see here, we have now components maybe going directly with micro vias on the flex layer, and we are going here now on layer 2 over the flex area. The reason is we don't want any galvanic copper on this layer 2 because for dynamic application it's not perfect. On the outer layer we would have a galvanic copper on it. Then we are also using here an RA copper. It's a rolled anneal copper, which is has better bending behaviors on this flex layer 2. And the flex area in this case is also covered with a cover lay. So it's also a better performance with a cover lay, or if you have a dynamic bending application, you should always use a cover lay instead of a flexible solder mask. And here you could see the cross section of this PCB. You could see here the flex. This is then the FR4 material under, and you could see here the lift off. There we are. One more option what we see here is we have here an extra cover lay also on the rigid part, which you could see here. With this cover lay, also you could cover vias, other blatings and so on. What is the reason for this? So it gets an extra insulation on the outer layer. Maybe it's directly in contact with the housing. We could put here a cover layer on it, and you have then a better dielectric strength here. The last option which I would speak about today is our SIP connectors. As you can see here, so SIP contact, So ZIF means zero insertion force contact. So our main problem mainly is with some connector data sheets. We as PCB supplier, we need a thickness tolerance of plus minus 50 micron, yeah. But we have a lot of specification which is less than this, I would say 50 micron specification. And there, I would say every PCB supplier gets problems to fit this tolerance. Yeah. What is the advantage now with using this 2F-xRi technology? So we could contact here now in the ZIF area directly, maybe a ground, or the signals are running on layer 2. We could contact here directly by microvias this layer 2, and it's much easier for us compared if the flex would sit, I would say, in the middle of the PCB. If you are now using microvias, then don't place them, I would say, directly here. Well, later this spring contact is contacting this contact, then put the microvias more in this area. So then we don't need to fill this microvias by copper. Yeah. Here you could see 2 examples. So what we are commonly doing is cutting this laser, this ZIF contact by laser. And it's also getting maybe such snap-in hooks as pull-out connection. So it's getting here different variants of ZIF contacts. So everything here is also possible, also with the small control tolerances or small radius here, because of cutting it by laser process. Good. So we come to our next poll. You have now heard a lot or some options, advantages of this 2F-xRi technology. Now I wanted to know if you see in your company any applications, yeah, if you could use this technology. So you could have here multiple answers. So it's maybe optimization of running projects on the one side, in the performance, on the other side, costs. You have planned use in current projects, or maybe for future projects, or the last thing is that you have no need for this technology. Okay, then we start the poll.
Okay, so please make your choice again. And we have passed 20% already, 30%. We target again around about 90% of voted participants. So actually we've got 70%. So we will wait around about another 10 seconds for this poll. Okay, 80%. So now let's have a look. I will close the poll and show you the result again. So this is the result. Thanks for that. So 23% see optimization potential in terms of performance as well as in optimization of costs. So 23% for both. 33% have planned this stack up in current projects, and 61% may possibly use that for future projects, and only 5% do not actually see need for this technology, which may change finally.
Hopefully.
Hopefully, yes. I think this was a successful webinar based on these results. Thank you very much for that.
Okay, then thanks for this poll. Then we come to our last slides. So here now a summary, the advantages which we spoke today in our webinar. So at the end we have the main thing in the one is the performance. Oh, sorry, it was too fast. The one is the performance and the other is the cost. So in general, I can say regarding the performance, standards are generated. So we have standard stack, standard design rules for this technology. One more thing is regarding the impedances is that we could go one-to-one over this flex area without any bladed through holes, or contacting the second layer by microvias to contact the ground reference, or the signal routing is on layer 2. As you also have seen, these HDI combinations are possible with this technology, and you also have a lot of mechanical options like lift off SIG contacts, and also suitable for dynamic bending stress. And at the end, regarding the costs, so if you need more than one layer in the flexible area, it's lower costs, I would say, compared to the flex in the middle of the PCB. So last slide is regarding the capability of Würth Elektronik's flex rigid PCBs. So in general, we say 1 or 2 flex layers. The flex could be on the outer layer. If you have more than 2 layers in the flexible area, it must be inside. Then we also have technologies like semi and band flex. These are based on FF4 material, so not on polyamide. We have different materials, so which could be combined with this flex rigid technology. We have standard stack, we have non-standard stacks. It could be HDI combinations, so contact us here if you don't find the stack on our website. We have different options with the impedances, cover layer, outer layer, lift off areas, and SIF contacts. And at the end, you could have PCBs at us in express service, and also from samples up to large series. Good. This was my last slide now.